So this is where we have left last class. In the last class, we have 3 more equations for the Fdtd discretization. So this is the equation. I have some problem with the pointer here, so I'll not use laser pointer today. Okay, so this is one of the equation. Dou x by dou t is equal to -1 by mu naught dou z by dou y minus dou ey by dou z. So now, if you remember the Yi's Fdtd cube yesterday, x was in the phase of yz phase. So y and z will have half integer space steps. So q plus half, r plus half, q plus half, r plus half. And x will have integer steps, so p and q. P here, p is the running index for x. And Mental is calculated in half integer times steps, so n plus half and minus half divided by delta t. So right hand side, let us look at it. You should be able to write all of this equation on your own. So let's look at dou ez by dou y. So dou ez by dou y, ez is at the center of the edges along the x-axis. So z component or z running index will be half integer space step. So r plus half. And we are doing differentiation with respect to y. So pq plus 1, pq divided by delta 1. Q plus 1 minus q would give me, divided by delta y, give me del ez by del y. Similarly, del ey by del z you have here. So ey is center of the edges along the y-axis. So q plus half. Partial derivative with respect to z. So r plus 1 r divided by delta z. And p here. So you can write like this. Similarly, you can look at this equation here. Del sy by del t. So sy is at the center of the face in the xz plane. So x and z would be half integer space step. So p plus half, r plus half, p plus half, r plus half. Y would be integer q here, running index for y is q. Then n plus half, n minus half divided by delta t. Similarly, del ex by del z, del ex by del z is here. So ex is the center along the edge along the x-axis. So p plus half. Partial derivative with respect to z. So r plus 1 minus r. Similarly, you can look at del ez by del x here. Ez is the center along the edges along the z-axis, so r plus half. Partial derivative with respect to x, so p plus 1 minus p. Similarly, you can have del ez by del t is equal to -1 by mu naught del ey by del x minus del ex by del y. You can write it. Look at this iz. iz is at the center of the face in the xy plane. So x and y running index would be half integer space step, p plus half, q plus half, p plus half, q plus half. And it's a time derivative, so n plus half, n minus half divided by delta t. Similarly, del ey by del x. So ey is at the center of the edges along the y-axis, so y running index q would be half, q plus half here. So then partial derivative with respect to x, so p plus 1 minus p divided by delta x. Similarly, del ex divided by del y is basically Ex at what is Ex is the center of the edges along the x-axis. So p plus r, partial derivative with respect to y. So y running index is q plus 1 and q here. This should be q plus 1 here. And look at the time here. So electric field is calculated integer time steps. You have n here in between n plus half and n minus half for the magnetic field. So that's all about the 3D Fdtd update equation. We'll run this, if time permits, we'll run this demo and see if we have a cube, cavity cube, metallic cavity cube. So you have a cube with metallic walls, then you'll see that there's some resonance. It's a waveguide cavity, let's say rectangular waveguide cavity, or let's say circular waveguide cavity. So those kind of cavities with all metal walls will have some kind of resonance that can be done using the simulation. This is a program which will give demonstration after this lecture. Then you'll see that there is some peaks in the frequency response. So once you have the time domain response, you take the Fourier transform, then you can see frequency response. Then in the frequency response, there are some peak. It's basically for different modes of the cavity. So these are some of the possible modes: T0, 101, T011, T201. So all these modes you can see after you do the Fdtd simulation. So here one thing you need to worry about is discretization. See, let's say I want to do Fdtd simulation of a cube. So how do I do the discretization for different fields? How and where should I calculate the fields? Let's say if I want to calculate fields Ex, this is the x-axis. So Ex is at the center of the edges along the x-axis. So you are calculating Ex here at the center, Ex here at the center of the edges along the x-axis. So how many calculations you need to do? You need to do, let's say 1, 2, 3. 1, 2, 3 for one along this direction. Along this direction again you have 1, 2, 3. Then along this direction you have 1, 2, 3, 4, 5. So 3 into 5 into 3. This many calculation you need to do for the Ex. Similarly, if you want to find Ice-X, then Ice-X is at the faces of the cube, which is in the YZ plane. So YZ plane is this is YZ plane. X is along this direction. The vector would be directed along this x. X would be directed along this direction. We are calculating it at the center of the faces which are in the YZ plane. So this is YZ plane. So how many we need to calculate? So 1, 2, 3, 4, and 1, 2. So 1, 2, 1, 2, 3, 4. So 4 into 2. Again, how many of them phases are there? 1, 2, 3, 4. So 4 into 4 into 4. 4 into 4 into 2 is that many calculation you need to do for discretization of a cube like this. So this calculation is going to be different. So because of this, when you put it in the for loop would be different for Ex as X. So you need to be careful when you write the Fdtd program. The for loop calculations, how many for loops you have to go would be different for this, and this. Similarly, if you want to calculate Ey, so this is y-axis. So at the center of this along the y-axis of the cube. So you have 1, 2, 3, 1, 2, 3, 4, and 1, 2, 3, 4. So 4 into 4 into 3. Let's say if you want to calculate xy, it's at the center of the faces in the xz plane. So this is in the xz plane. This is the center. How many of them I need to calculate? 1, 2, 3, 1, 2. 3 into 2. 1, 2, 3, 4, 5. So 3 into 5 into 2. That many we need to calculate. So the for loop you need to worry about properly. You have to write the for loop. Let's say if you want to calculate Ez is the center along the z-axis, edges along the z-axis. So 1, 2, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5 into 4 into 2. That's what you need to calculate. For Iz is at the center of the faces in the xy plane. So 1, 2, 3, then 1, 2, 3, 4, then 1, 2, 3. So 3 into 4 into 3, that many you need to calculate. Okay. So that's about the Fdtd, basic Fdtd. So 1D Fdtd, 2D Fdtd, and 3D Fdtd. So now the problem with Fdtd is that if you want to solve the fields everywhere in space, you have to find the fields in infinite space. You have to find the fields in infinite space. And that is going to take a lot of time. So if you are having infinite space, you calculate fields everywhere in infinite space, it's going to take infinite time. So that's not practical. So what we do is we usually truncate the solution space to a finite space. We enclose the whole solution space inside a box. Most of the time when you write a Fdtd program, you enclose the solution space just inside a box. Let's say you want to do the simulation for antenna, you keep antenna at one particular location with the origin, and you actually draw a box and you apply some kind of boundary condition on the box so that simulation is not getting disturbed. So that is similar to what you usually do in antenna measurements. In antenna measurements, this is one antenna you want to make measurements. What you'll see is in the walls, in the ceilings, and in the floors, you put these wedges here. So this kind of wedges, actually, what is the purpose of putting these wedges? If you have done antenna measurement, this is called an Equi chamber, quiet zone, where you do antenna measurement, and these wedges are put on the walls, ceilings, and floors, so that any signal which is gone to the wall, ceiling, or floors will not get reflected back, and this antenna should not capture it. So if any signal is reflected back, it captures it. It is going to interfere with the signal which has been transmitted from the transmitter. Transmitter, you usually put it line of sight communication between transmitter and receiver. So this is receiving antenna is the antenna under test, AUT, or DUT, device under test. So you keep transmitter here, let's say usually horn antenna, you send a signal, you want to measure it in different plane, E plane and S plane. So signal which is gone from transmitter should directly come to the receiving antenna. It should not come after reflection from the wall, ceilings, or floor. It's going to interfere. That's called multipath. That's going to create a lot of difficulty in the measurement. So we put this kind of wedges in the walls, and it will actually absorb the waves. So there won't be any kind of reflection. So that same idea people has done in the Fdtd simulation. That's what we're going to see. You enclose the antenna or any device you want to do the Fdtd simulation, and you put some boundary condition on the walls of that box. You are enclosing the antenna or any device you are doing the simulation, and that box is actually made up of some layer which is called perfectly matched layer. So as the name suggests, it is perfectly matched. There won't be any kind of reflection. It's an artificial material, and you do not have practical material which will actually absorb all the waves. An Equi chamber is one example where you absorb some of the waves, but there will be still some reflection. And if that reflection is minimal, then there won't be much error in the experiment you are doing. But perfectly matched layer will absorb all the waves, irrespective of frequency, polarization, and angle of incidence. You can design this artificial material when you do the simulation, and it will absorb all the waves. So how do we do that? So how do we design this perfectly matched layer, which is actually a layer you put on the boundary box so that there is no reflection? So let us consider source-free Maxwell equation. Curl of E is equal to minus j omega mu h. Let's go back to the Maxwell equation. Curl of H is equal to j omega epsilon E. And divergence of D is equal to 0. Divergence of D is equal to 0. Source-free region, so we don't have any charges. We don't have any kind of sources here. So the only thing is that now we are actually analyzing this Maxwell equation in another coordinate system, which is called stress coordinate system. Stress coordinate system. What is stress coordinate system? You have stress the x-axis, y-axis, and z-axis. You can either increase it, you can either shorten it. So you need to multiply by a scale factor to the x-axis, y-axis, and z-axis to get the scale coordinate system. So in the scale coordinate system, your del operator, I have written it intentionally stress. It has been stress. So delta stress is 1 by sx del by del x hat plus 1 by sy del by del y hat plus z hat 1 by sz del by del z. So I have actually divided by one scale factor here. For the x-axis, it's called sx, and for the y-axis, it's called sy, and for the z-axis, it's called sz. So this is the stress del operator. So now you consider a simple plane waves. Plane wave will have electric field in a far field of the form E naught exponential minus jk dot r. K is the wave vector, r is the position vector. E naught will decide the polarization of this electric field vector. Similarly, magnetic field will also have IC is equal to H naught exponential minus jk dot r in the far field of the source. We have plane waves. K dot r is simply kxx plus kyy plus kzz. Kx is the x component of k vector and ky is the y component of k vector and z is the z component of the k vector. R vector will have x, y and z as the coordinates. So that's the usual stuff we have here. So now let's see something in the next slide. So now for the plane waves, you can replace all the del operator by jk, then you get this equation for the plane waves. K stress cross product with electric field is equal to omega mu h. K stress cross product with magnetic field is equal to minus epsilon E. You can easily derive this. I think I have discussed this in one of the classes, maybe last semester. K stress dot epsilon E is equal to 0. K stress dot mu h is equal to 0. Then what is this K stress? Stress K vector is simply Kx by Sx, Ky by Sy, Kz by Sz. We have divided by scale factor Sx, Sy and Sz in the Kx, Ky and Kz. So this is a K stress vector. So now surprisingly, when I do dot product of K stress with K, what I have is Kx by Sx whole square plus Ky by Sy whole square plus Kz by Sy. And this is the Sz whole square. So now surprisingly, if I take Kx is equal to Ksx sine theta cos phi, Ky is equal to Ksy sine theta sine phi, Kz is equal to Ksz cos theta, then what you can observe is this scale factor Sx and this Sx will cancel out, Sy and Sy will cancel out, Sz and Sz will cancel out. And finally, what you can observe is when I do dot product of K stress with K stress, if I take this solution, then it's equal to K squared, that of the free space. Even in this stress coordinate system, if I have chosen my Kx, Ky and Kz according to this relation, then the amplitude of the K vector in the stress coordinate system and in the original coordinate system is not changing. This is a point to be noted. In the stress coordinate system also we still have the same magnitude of the K vector, K stress with that of the original problem. Just look at it, for example, any wave which is propagating along the positive x-axis. How do I write? Exponential minus jkxx. What was our kx? Kx were ksx sine theta cos phi x. So now, if I have this scale factor sx, I can take any kind of scale factor because we are in the simulation domain. So when we want to implement it, then only we need to worry about what are the possibilities. But here, when we are doing simulation, I can assume that this scale factor has real part and imaginary part. Is a complex number. Real part is positive and imaginary part is negative. So real part of Sx I have denoted by S dash and imaginary part by S double dash. And you can clearly see that this is a negative imaginary number we have here. So now this minus j and minus j, when you multiply it, what do you get? Minus minus plus and minus j and minus j, you get minus. So what you are getting exponential minus s double dash sine theta cos pi x. So any wave which is having some value like exponential minus s double dash, where s double dash is a positive number, this is a attenuating wave along the x-axis. So we are having so the first term will actually give you the phase propagation, but second term actually when you multiply z and j you get minus 1 and minus 1 become plus, so it becomes minus s double dash sine theta cos pi x. So it's a wave propagating along the attenuating along the x-axis. So we have a highly attenuating wave along the x-axis. So I can attenuate the wave along the x-axis. So this is another point we need to note down. First point was that K stress vector amplitude in the stress coordinate system is having same as that of the original problem, which is the K vector. And another thing is that if I have a wave which is propagating along the x-axis, I can attenuate the wave by just taking my scale factor which has real part positive and imaginary part negative. So I have a wave which is attenuating, highly attenuating along the x-axis. I want to attenuate the wave along the x-axis. So then I can have to take this scale factor simply as S dash minus JS double dash. So look at the wave impedance. Wave impedance is E modulus of E divided by modulus S. You can also write this as omega by K stress. And I already emphasized that K stress and K vector is same. So here our wave vector in the stress coordinate system and that of the original problem is same. So that means original problem, some signal are propagating. It once enter into this PML layer, it is still having the same wave impedance. There won't be any kind of reflection. So that's why we call it perfectly matched layer. So the original problem solution space where wave was propagating was having eta of omega mu by K. And inside the PML layer also we have omega mu by K stress, and both of them are same. That's why it's perfectly matched. Impedance is not changing from the original solution space into the PML layer. So there won't be any reflection. And this term actually will also try to attenuate the wave along propagation along x-axis. We can do it for y-axis and z-axis also later on. So let's say this is the typical example. We want to do Fdtd simulation of the object here. This object here. This is 2D case with this x-axis. This is y-axis. So if you want to do simulation for infinite space, you have to have infinite time. So we don't have time for infinite time to do the simulation. We want to finish as soon as possible. So now what we do is we enclose this inside a box. And if I told you this box should have some properties which will actually absorb all the waves. It should not have any kind of reflection so that it will not interfere with the waves which was transmitted from this object here. So we should have, in other words, we should have a PML layer here. So we have already seen that in the PML layer, we use the stress coordinate system and wave impedance for this PML layer is same as that of this original problem. So we'll not have any wave reflection here. Then after that, once the wave enters this PML layer, I want to attenuate the wave. So if I want to have wave attenuation along the y-axis, then I just take scale factor as S dash minus J S double dash. Imaginary part is negative. So this will attenuate the wave along this direction. Along this direction also. If I want to have wave attenuation along the x-axis direction, I just take scale factor S dash minus J S double dash. So Sx is S dash minus J S double dash. Imaginary part is negative. What happens to the corners? Corners will have wave which is propagating from x-axis as well as from y-axis. So there we need to take the scale factors Sx and Sy as S dash minus Js double dash. So all the corners will be taken care of. So this is actually PML layer where you need to have wave impedance of this stress coordinate system same as that of the original problem. Moreover, the scale factor should be taken such that imaginary part is negative so that we have highly attenuating wave along x-axis, highly attenuating wave along the y-axis, and in corners you need to have wave attenuation both in x and y plane. Okay. Then we have, so in the stress coordinate system, let us try to analyze it. We still have time. Okay. So how do I analyze the PML layer? There is something called Berenger's PML, which is called split fill. You need to split the fill. So let us look at the Maxwell equations. Maxwell equation is curl of E is equal to minus J omega mu H. I want to analyze in this for the PML layer. So I use the stress coordinate system. Del stress cross product, curl of del straight with E is equal to minus J omega mu H. So now this curl here, you can write it in the simplified form 1 by Sx del by del x cross product of S unit vector with electric field plus 1 by Sy del by del y cross product of y unit vector with electric field plus 1 by Sz del by del z cross product of z unit vector with electric field. So you can simplify this curl, you can express it in this form. And because of the stress coordinate system, I also have 1 by Sx, 1 by Sy, 1 by Sz. Otherwise, even for normal curl of electric field, you can write it in this form, del by del x, x hat cross with E and so on. You'll have 3. So now, since I have this 3 terms here in the left hand side for the curl, I can split the magnetic field in the right hand side. This is the right hand side magnetic field. So I have three terms here, first term, second term, and third term. So magnetic field also can be splitted into three terms in the right hand side to equate it to this, this, and this. So that's what the process is, split field. Splitting the magnetic field. Magnetic field, let's say if I have ISX plus ISY plus ISZ. So then I can equate the first term with the ISS term, and I can equate the second term with the ISY term. I can equate the third term with the ISZ term. And what was the purpose of PML layer? We want to attenuate the wave. So I actually intentionally take Sx as 1 minus j sigma by omega epsilon, Sy as 1 minus j sigma y by epsilon, Sz as 1 minus j sigma z by omega epsilon. So here imaginary part is negative. So imaginary part is negative for Sx, also Sy, also Sz also. That is what you need to worry. So if you take imaginary part negative, then you'll have highly attenuated wave along x-axis, y-axis, and z-axis. So that's what we want in the PML layer. So this Fdtd update equation we're going to write is for the PML layer. So I need to have scale factors with negative imaginary part for both x, y, and z. What was our equation? Del by del x, cross product of x unit vector with electric field. And what do we have in the right hand side? Right hand side, j omega Sx, j omega mu. So I have actually taken this scale factor to the right hand side. So what I have is minus j omega mu Sx Sx. What is Sx? Sx is 1 minus j omega j epsilon j sigma x divided by omega epsilon. So now I simplify it. So whenever I have a j omega, so I actually work in the time domain. So j omega is in the phasor domain. So I need to replace it by the time domain. J omega can be replaced by del t. Then second term you have here. Similarly for the second term and third term. Second term, I used to have 1 by sy here. I transfer it to the right hand side. It will become sy here. Sy j omega term I can replace it by del t. Similarly for this term also I can transfer sz to the right hand side and replace sz as 1 minus j sigma z by omega epsilon. J omega term can be replaced by del t. So this is the final equation we have for the splitting the magnetic field. So you can also split the electric field for the next Maxwell-Curl equation. Del stress cross product with H is equal to j omega epsilon E. So here I will have on the left hand side this first term, second term, third term. I transfer the 1 by Sx to the right hand side, 1 by Sy to the right hand side, and 1 by Sz to the right hand side. And split the electric field. We have this electric field and I split it into x, split x, split y, split z. So this is first term is for the split x, second term is for the split y, third term is the split z. And whatever term del by del j omega term I can replace it by del t because we are working in the time domain. So first term will del t here, del t here, del t here. Second term as usual is like this. So we can use this split electric field for update equation. So, okay, that was for the 3D case. We'll have 6 equations, 6 split field equations. We need to discretize it for the Fdtd for the PML layer. So Fdtd for PML layer for 3D case is little bit involved. We'll start with the simpler case of 2D case. For example, if we consider 2D TMZ problem, TMZ means we don't have wave propagation along the z axis, so del z is 0. TMZ, magnetic field doesn't have any z component, Iz is 0, so magnetic field will have X and XY component, Iz is 0, and once magnetic field has X and XY, electric field will only have Ez because electric field and magnetic field are perpendicular to each other. In that case, Ex and Ey is 0. So now we can solve this split field Berenger's PML for 2D TMZ problem here. So what was our equation? 1 by Sx del x, x hat cross product with electric field is equal to minus j omega mu I split x. Similarly, second, third, and so on. This is what we need to solve. So looking at this term here, cross product of x unit vector with electric field. Electric field has only z component. X cross with z will give direction along the y-axis. So that means this magnetic field split x for this 2D TMZ problem would be along the y-axis. So I can write split magnetic field split X as Y hat X Y. Similarly, when I do cross product of Y unit vector with EZ, electric field has only Z component. Y cross Z is basically, it will give you only X component of the magnetic field. So I can write I split Y is equal to X and X. So this makes physical meaning here for this particular problem, but usually this split X, split Y, and split Z doesn't have any physical meaning. But here for this 2D TMZ problem, it is making sense. So I split X is IY and I split Y is IX. Looking at the last term here, Z cross with EZ, electric field has only Z component, it will become 0. So this term will become 0. So we have much more simplified version of this equation here for the 2D TMZ problem. Okay, so what is the equation? Del by del X, X hat cross product with E. E has only EZ Z hat. So finally you can simplify it is minus dou EZ divided by dou X Y hat. And as you know that this I split X will have only Y component, it will become minus J omega mu SY Y hat. What was SY? SY was 1 minus J sigma Y by omega epsilon. Then whatever G omega term, I will replace it by del T, and other remaining terms are here. So this is the equation. Similarly, you can look it for del by del Y cross product with E. E is EZ Z hat, it will become del EZ by del Y X hat. And I split Y will become I X hat. I have already discussed it in the previous slide. And you replace SY by 1 minus sigma Y divided by omega epsilon, then J omega term you can replace it by time derivative del by del T, then this second term here. Similarly, you can also do it for the last equation del by del Z, Z cross E is equal to 0, because you know that I split Z is 0. We have done that in the previous discussion. Similarly, you can also do split fields for magnetic fields for 2D TMZ problem, and it turns out to be this equation here, epsilon del Ez by del X equal to mu epsilon del Icy by del T plus sigma X mu Icy. Similarly, these two equations you have here, you can do the same thing I have done for the split electric field. You can do it for a split magnetic field also. You can also split electric fields for TMZ problem. Electric field has only Z component. TMZ problem, then magnetic field doesn't have any component along the Z axis. So Ez here would be Ez Z hat, and magnetic field can have X and Y component. And this X cross Ice vector will have Ice X and Ice Y. So when you do cross product of X with H, what do you get? This term will become 0. You just get Y component. You just get X cross Y is Z component. Similarly, you do Y cross H, Y cross X will give me Z component. Y cross Y will give me 0 component. So now you do the split electric fields. What do you get? Del by del X of X cross H is basically del X Y with del X. Then right hand side, after putting Sx is equal to 1 minus J omega, 1 minus J sigma X divided by omega epsilon. You can simplify it. Similarly here also you can do it. So finally, electric field will have only Z component, magnetic field will have Ix and Xy component. You can solve it from this equation. So split field for electric fields for 2D TMZ problem also you can do it similarly. And here you have splitted the electric field. Electric field has only one component, Ez. So we split electric field Sx and we split electric field Sy. So you can write this equation here. I think you may be having a lot of problems. I'll wind up here.